Okay, here's another problem. A company wishes to manufacture a box with a volume of 52 cubic feet. It's open on top and is twice as long as it is wide. So just remember that there's no top. So it's open on top. Alright, so find the dimension of the box that can be produced using the minimum amount of material. So basically, we're given two secondary equations. Our primary equation, let me just go ahead and show you the primary equation. Our primary equation is we want to minimize the area. So if you look over there at the box, there's going to be 5 pieces that we got to deal with. We've got to deal with this front side, which is L times H, and there's also a matching back side that's L times H. So therefore we have 2LH. And then we've got this side over here, that's W times H, and then we've got a side opposite it that's W times H. So we got 2 WH's to deal with. Well, then we got the bottom of the box. The bottom of the box, the dimensions are L and W, so that's just LW. Remember, we're not doing the top. So basically, we have 2LH plus 2WH plus LW. All right. Well, we know that the length is equal to twice the width. That's what we were given. We're also given that the volume is 52. So we know the length times width times height is 52. So let me show you how we're going to manage this. All right. So since length is twice the width, I'm going to replace the length here with 2W. So therefore, I get 2W times WH equals 52. Well, that's the same as 2W squared equals 52. So now I can solve for H in terms of W. So if I divide 2W squared into 52, I actually get H equals 26 over W squared. So now I've got L in terms of W, I've got H in terms of W, and I can go to my problem and make some substitutions. So go to my problem. Everywhere there's an L, replace it with 2W. So that would be here and here. And everywhere there's an H, replace it with 26 over W squared, which that's going to be here and here. Now, if you simplify that, you're going to get 2 times 2 times 26, which is 104 over W, because actually this W will cancel with W squared, giving you W. And then the same thing here, this W cancels with this W squared, giving me W in the denominator. But here I have 2 times 26 is 52. And then here I have 2W squared. So basically, if I add these two together, I get 156 over W plus 2W squared. But so I can differentiate that, instead of saying 156 over W, I'm going to write it as 156 times W to the negative 1 plus 2W squared. And then when you take the derivative, you get minus 156W to the negative 2 plus 4W. And then we set that equal to 0 to solve it. And so what I'm going to do is similar to what I did in the previous problem. I'm going to multiply everything by W squared so I can cancel that W to the negative 2. So if I multiply this by W squared, I just get the negative 156. If I multiply 4W by W squared, I get 4W cubed. And of course, 0 times W squared is 0. And I went ahead and factored a negative 4 out of here. And I got 39 minus W cubed. And so if you set that equal to 0 and solve it, you'll get W cubed equals 39. And then so W must be the cube root of 39. So W is the cube root of 39, which is approximately 3.4 feet. And then the length is twice that, so that's going to be approximately 6.8 feet. And then the height, remember, is 26 over W squared. So 26 over 3.4 squared would be about 2.25 feet. And so there's the dimensions that will actually minimize the amount of material that you use to create that box. Okay, I'm going to let you pause the video and read this problem and just use this as a practice problem. And then you can, when you're finished, you can restart the video and check your answer and then move on in the video. So I've got this one worked out for you. So you can just use it as a practice problem. And I'm going to move on to the next problem. Okay, so on this problem we have a page of 30 square inches of print, and the margins at the top and bottom are 2 inches, where the margins at the sides are 1 inch wide. And so what dimensions will minimize the amount of paper used? Well, let's draw our diagram. You know that the dimensions at the top and bottom are 2, so these dimensions are 2 here and here, and these dimensions on the sides are 1, so ignore the magnitude there, even though it doesn't look like it's twice the size on the dimensions. Okay, so basically I'm going to call the entire width of the paper X and the entire length of the paper Y. Well, if I'm going to have dimensions 2 here and 2 here, then in the print area, that would be this Y value minus 2 here and minus 2 up here. So the height of that print area would be Y minus 4. And the width of that print area would be X minus 1 here and minus 1 here. So the dimensions of the print area would be X minus 2 and Y minus 4. Well, we know that we're given that area must equal 30. Okay? So that area has to equal 30. Well, let me go back into what we want to our primary equation. Our primary equation is to minimize the area used, and the area is going to be X times Y. So the area of the paper is X times Y. So that's what we want to minimize. Now, what I've got here is I've got a way now to solve for Y in terms of X, because now if I take this and divide by X minus 2, because I know X minus 2 times Y minus 4 has to equal 30, because this print area has got to equal 30 square inches. So that product must be 30. Well, now if you divide by X minus 2, you get Y minus 4 equals 30 over X minus 2. And then if you add 4, you get Y equals 30 over X minus 2 plus 4. And now I can take that value and plug it back in here for Y to eliminate the Y. So now I get X times 30 over X minus 2 plus 4. And so the area is 30x over X minus 2 plus 4x after I multiply. Well, I'm going to go ahead and take the derivative of this. I use the quotient rule on the first term, and then of course the derivative 4x is just 4. So this is the derivative that I got. And then you set that derivative equal to 0, and actually you can move this term over to the other side since it's a negative, and you'll get a positive. And so I get this. And then when you cross multiply here, you're going to get 4 times X minus 2 quantity squared equals 60. And then divide by 4, you get X minus 2 squared equals 15. So X minus 2 equals plus or minus the square root of 15, but the minus square root of 15 doesn't make any sense. So X equals 2 plus the square root of 15 is your answer. So that's actually about 5.9 inches. And then that's the X value, or the width of the paper. Then to get the height of the paper, you just plug in this value. You have 30 over 5.9 minus 2 plus 4, and that's going to give you the actual width of the height of the paper, which is about 11.7 inches. Okay, I'll let you read this problem, and you need to pause the video if you want to. I'm going to go ahead and just go straight into the solution. Okay, so basically I'm going to let P be the price of an apartment, and I'm going to let X be the number of occupied apartments. Okay, well, from the information we're given up here, we know that when the price is $5.40, X is 50. But if we increase the price to $5.70, then we know that the number of apartments will drop to 49, because we'll lose one apartment. So using that information, I can get the slope. So if I take P2 minus P1 over X2 minus X1, 570 minus 540, or 49 minus 50, I'll get negative 30 for the slope. And then I can use this formula, this slope point slope formula to actually get a relationship between the price and x. So all I have to do is use the slope now, negative 30, and then one of these points. I'm going to use the point 540 and 50, and then so I get p minus 540 equals negative 30 times x minus 50, and then so p equals, you can do the algebra there and get p is negative 30x plus 2040. Now all that did is gave me a function for the price. For revenue, remember revenue is x times p. We did a problem similar to this earlier. So now just multiply x times this and you'll get minus 30x squared plus 2040x. And the cost, if you go back and look at the problem, the cost is 36x. Now what we want to do is we want to maximize profit, but profit is revenue minus cost. So if you take this function, and if you take this function and subtract this function, revenue minus cost, you're actually going to get minus 30x squared plus 2004x, and then that's their profit function. And then when you take the derivative of that, you get minus 60x plus 2004. And if you set that equal to 0 and solve it, you get about 33 units. So x is the number of units that actually maximizes your profit. And so if you plug 33 into your price function, you can actually get the price that you should charge. So you should charge a price of 1,050, and you'll only have 33 apartments rented, but that will maximize your profit. Okay, I'll do one more on this video, and I've got a couple of hard ones for the next video. Okay, so on this one, the points are y equals x squared plus 4. We've got a graph y equals x squared plus 4, and we want to find the points on that graph that are closest to 0, 8. So here I've done just a rough sketch of the parabola x squared plus 4, and I gave you where the point 0, 8 is. So basically I want to find the point on this parabola. Now remember, every point on this parabola, the x value can be represented as x, and the y value can be represented as x squared plus 4. So the distance between these 2 points, I can use the distance formula and say the distance is going to be the square root of x minus 0 squared, which is this, and then x squared plus 4 minus 8 quantity squared, which is this. Well, if you square that, if we minimize d squared, that's the same as minimizing d. So whatever minimizes d squared will minimize d. So I'm just going to square that and get rid of the radical. Now if I simplify the algebra here, you'll actually get this polynomial, okay, which actually simplifies to this polynomial. And now if you take the derivative of this polynomial, you get 4x cubed minus 14x. And if you factor that, you get 2x times x squared minus 7. And that actually has 3 critical numbers, 0, minus square root of 7, and plus square root of 7. And if you apply the second derivative test, you can see that at plus or minus square root of 7, you're going to get a minimum for d squared. So that's also going to be a minimum for d. And then if you want to figure out what the y value is, all you have to do is plug plus or minus square root of 7 into the function, and you'll get 7 plus 4 in each case. So you'll get the point square root of 7, 11. So this point is actually square root of 7, 11. But there's also another point over here that's also the same distance, and that's minus square root of 7, 11. So those are the points that actually minimize the distance between the point 0, 8 and this parabola. And so that's an interesting problem. Okay, like I said, I've got a couple more rather difficult problems, at least I think they are, that I'll do on the next video, and then that will complete this chapter.